In this video, we're going to explore a way to understand how a differential equation behaves without actually solving it. We'll build something called a slope field, learn how to read a slope field, and then use the slope field to understand the solutions of a differential equation. We've seen before that we can use tangent lines to give us reasonably good local approximations for functions. A slope field takes the information inherent in a differential equation and uses it to generate a large number of tangent line approximations. Following the paths created by these approximations, we can then sketch in possible solutions for our differential equation. In other words, the solutions to the differential equations follow the flow of the slopes of the tangent lines we've drawn. Building a slope field by hand is a three-step process. First, we're going to choose appropriate grid points for the field in question. Then we'll compute the slope at points on that grid. And then last, we'll draw a tiny segment with that slope. Let's take a look at a specific example. So if we want to create a slope field for the differential equation y prime of t is equal to t minus y, we have to start off with a grid. I'm going to use the values between -2 and 2 in both directions. So I'm going to draw myself a 5 by 5 grid. I'm going to consider this part of the grid to be the t values and this part of the grid to be the y values, so that'll translate easily to our graph. And here we're going to have t as -2, -1, 0, 1, and 2, and we'll do the same for y. Within each square, we're going to calculate y prime for the given values. So in other words, if we choose this square down here, we have t equals -2 and y equals -2. We know that y prime is t minus y, so t minus y is -2 minus -2, which is 0. So we're going to put a 0 in that box. Then we'll just proceed doing t minus y for each of the values within our box. So we move over to the right, we get -1 minus -2, that's +1. 0 minus -2 is +2. 1 minus -2 is 3, and 2 minus -2 is 4. We'll move up to the next row. Starting with t equals -2, we get -2 minus -1, so that's -1. Then we have -1 minus -1, 0 minus -1, 1 minus -1, and 2 minus -1. Moving up another row, -2 minus 0, -1 minus 0, 0 minus 0, 1 minus 0, and 2 minus 0. -2 minus -2 minus 1, -1 minus 1, 0 minus 1, 1 minus 1, and 2 minus 1. And last but not least, we have -2 minus 2, -1 minus 2, 0 minus 2, 1 minus 2, that should be -1 minus 2, and 2 minus 2. So we can see some patterns here. We can see that when the t values are bigger than the y values, our slopes are positive, which means we're going to have upward facing slopes. And when our y values are bigger than our t values, our slopes are negative. We can now take these slope values and we can put them on a set of axes and consider them as the slope of line segments. So in other words, if I draw a graph that looks like this, where I have -2, -1, 1, 2, with 0, 0 obviously at the center, I now know that at the point -2, -2, I'm going to draw a segment with slope 0, so a horizontal segment. When I move over to -1, -2, I'm going to have a segment with slope 1. When I get to the point 0, -2, I'm going to draw a slightly steeper segment with slope 2. Moving over one more, my segment gets even steeper. And then last, I draw a very steep segment with slope of 4. Now I'm going to repeat that for when y is equal to -1, I get a slope of -1. then a slope of 0, a slope of positive 1, a slope of 2, and a slope of 3. When y is 0, I start with a slope of negative 2, then a slope of negative 1, a slope of 0, a slope of positive 1, and a slope of positive 2. I then have a slope of negative 3, a slope of negative 2, a slope of negative 1, a slope of 0, and a slope of positive 1. Lastly, I have a steep slope of negative 4, a slightly less steep slope of negative 3, then negative 2, then negative 1, and a slope of 0. Our last job is to interpret the slope field by tracing along the flow of these tangent line segments. So we can choose one. We'll start maybe here with this segment, and we're going to trace it. It's pointing downwards. We come to the next one. It tells us to veer off to the right. We come to the next one, and we end up following along the segments that have slope of 1, which point together, and we see that our solution curve looks something like that. We can do something similar down along the bottom. If we track this one here, it's pointing us upward. We bump into the ones that have a slope of 1, and we trace along them to get a solution curve that looks like that. One thing to note if you're drawing in multiple solutions is that these solutions won't cross each other. You can see that the process for doing these by hand can be a little bit laborious. Fortunately, there are tools to do that. This one is one that I particularly like. It's a graph in Desmos. I'll drop the link in the comments, but it allows you to adjust the parameters so you can increase the number of segments, increase the length of the segments, and it also allows you to plot a curve with a given starting value on it. This one we're seeing here is the exact same slope field that we just generated by hand for x minus y. It's x minus y instead of t minus y, but it's the same curve. All right, let's take one more look at a slope field and figure out what kind of information we can gather from it. So here we have the slope field for y prime of 2 equals y minus 2. This is a first order linear differential equation. And we're asked to figure out for which initial conditions, in other words, when the t value is 0, are the solutions increasing, where are they decreasing, and where are they constant? So let's start with constant. We can see right along here when we have an initial condition of y equals 2, the slopes are all 0. This tells us here that we have a constant solution. Another term for that is an equilibrium solution. It's called that because the equation is not changing. It has reached a state of equilibrium. When we look above y equals 2, we can see that if we were to pick any initial condition, let's pick this one here, and we were to track those tangent lines, we would get something that looks like this, which is increasing. And that's going to be the case for any initial condition we pick where t is greater than 2, or when y is greater than 2. So we see that for y is greater than 2, our solutions are increasing. Similarly, if we go down below the axis and we pick some initial condition, so here we have y is about a little less than negative 1/2, and we track that solution, we're going to get a curve that looks something like that. And so for y less than 2, we have decreasing solutions. We'll see too that when we can't solve a differential equation, we can gather a lot of information about where the solutions are increasing, decreasing, reaching equilibrium, things like that. But also we can use a slope field, especially when we can generate using technology, to confirm what we might be able to figure out when we can in fact solve the differential equation. Let's summarize what we've learned here. We now know what a slope field is. We can build one by hand by calculating slopes at individual points and plotting them on a grid. We know how to interpret a slope field. In particular, we can use them to determine equilibrium solutions and when our solutions might be increasing or decreasing. And we have some understanding of why they're a powerful tool when the solutions are impossible to find algebraically.